ME204, Rigid Body Kinetics using Conservation of Energy. We've already talked about the different types of energy that are associated with a rigid body. For example, with kinetic energy, we have 1/2 the mass times the velocity squared if the object is translating, or 1/2 the mass moment of inertia times the angular velocity squared if the object is rotating. For potential energy, for gravity, we have mass times gravity times the height of the object from a particular datum. This value can be positive if the height is above the datum, or negative if the height is below the datum. For springs, potential energy, or stored energy, is represented by 1/2 the spring constant times the stretched length of the spring from the unstretched length squared. Let's look at this in terms of translation, rotation, and general plane motion. For kinetic energy, when an object is translating, we use 1/2 the mass times the velocity of the center of gravity squared. If it's pure rotation, then we have 1/2 the mass moment of inertia about the center of gravity times the angular velocity squared. For general plane motion, where we have both translation and rotation, we add both of these terms together. Or we can also shift our mass moment of inertia about a fixed point of rotation to get 1/2 the mass moment of inertia about the fixed point times the angular velocity squared. But again, this is only valid if O is a fixed axis. 1/2 mv squared plus 1/2 ig omega squared we can use anytime. For potential energy of gravity, this only occurs as translation and is mass times gravity times the height. For potential energy of a spring, in this course, we're only looking at translation, and it's 1/2 the spring constant times our change in length from the unstretched length squared. For work, with translation, it's a force times a distance. And for rotation, it's a moment times an angle, where the angle is measured in radians. Now that we have all the pieces, let's put everything together so that we can solve energy problems. Again, we'll talk about our financial account balance equation. We have an initial balance, we add deposits to that balance, or we take withdrawals away from that and end with a final balance. And again, the same is true with energy. For our work energy equation, we have an initial energy, we add or subtract non-conservative work from that energy to end up with a final energy. For our initial energy, we have kinetic energy and potential energy, and then we add or subtract our non-conservative work and end up with a final kinetic energy and a final potential energy. This can be represented with this equation. We now add in our 1/2 mass moment of inertia about the center of gravity times the angular velocity squared to both sides of our equation. So what happens now if we don't have any work? In this case, our initial energy has to equal our final energy. That energy transfers from one term to another, but the total energy is still the same. In this case, we have conservation of energy. Consider a Cub Scout Pinewood Derby car. A good understanding of energy can help us understand how to better design one of these vehicles. If we have a car at the top of the track, and then release this car, gravity pulls the car downward down the track, and our potential energy converts to kinetic energy. At the beginning of the race, we have potential energy. There's no kinetic energy because the car is not moving, but it has elevation. As it comes down the track, we lose some energy due to friction and air drag. There's friction loss in the wheel bearings. There's friction loss due to the car wobbling or bouncing on the track as it comes down the track. We also have rotational kinetic energy associated with the wheels. And finally, we have linear kinetic energy. Potential energy is good. The more potential energy that we have, the more kinetic energy we have at the bottom of the track. Friction is bad, wobbling is bad, and the rotational kinetic energy of the wheels is bad as well. Our linear kinetic energy is good. This is what contributes to the velocity or the speed of the car at the bottom of the track. The higher we can get our linear kinetic energy, the faster our car goes at the bottom of the track. To help us understand this, I'm going to choose some easy numbers. They're not representative of actual numbers, and this is not to scale. This is just for demonstration purposes. Let's say that we have a height of the center of gravity of car, represented by h, and that potential energy gives us 6 joules of energy for demonstration purposes. As it comes down the track, let's assume that we lose 2 joules to friction losses and wobbling. We lose 2 joules to rotational kinetic energy, and 2 joules is put into our translational kinetic energy. What if we could eliminate the friction? If that were completely removed, then that energy has to go somewhere. So some of it would go to the rotation of the wheels, and some of it would go to the translation of the Pinewood Derby car. So the car, in turn, would go faster. Now, what if I redistributed the weight towards the back of the car? So instead of having the weight at the front of the car, I put it in the back. Now my height increases. That would increase my potential energy. Let's say that it increases us from 6 joules to 8 joules. Now I have that much potential energy that can convert to either work or kinetic energy. Well, if we got rid of our losses due to friction, all of that energy would convert to our kinetic energy. So maybe we would increase our rotational kinetic energy to 4 joules, but we would also have some of that contribute to our translational energy or our speed of our car at the bottom of the track. So maybe we would have 4 joules. This in turn would make the car go faster. Now what if I could remove some of the mass of the wheels and change our mass moment of inertia so that they absorb less energy? If I can reduce the energy that goes into the rotation of the wheels, then that energy in turn has to contribute to the translation of the vehicle, and the car will go faster. Here's an example associated with conservation of energy. Let's say that we've got a 50-gram yo-yo with an inside peg radius of 5 millimeters, and it's released from rest and is allowed to drop. How far must the yo-yo drop to obtain an angular velocity of 80 radians per second? Let's assume that the radius of gyration for the yo-yo is k equals 20 millimeters. Well, let's first write our energy balance equation. We would have our initial energy, the work associated with it, and our final energy. We can now go through and ask questions of each of the terms associated with the mass that we're dealing with. Well, there's no springs involved, so we can immediately get rid of the spring terms. The yo-yo initially isn't moving, it's dropped from rest, so there's no translational component. And it's not rotating initially either, so we can eliminate that from our equation as well. If we place our datum at the bottom of the movement, then we can eliminate our potential energy due to elevation of the yo-yo on the right side of the equation. There are no external forces acting on the yo-yo, and no external moments being applied. So we're left with the mass of the yo-yo times gravity times its initial height is equal to 1/2 the mass moment of inertia about the center of gravity times the angular velocity squared plus 1/2 the mass of the yo-yo times its velocity of the center of mass squared. Our mass moment of inertia is equal to the mass times the radius of gyration squared. So in this case it's 0.05 kilograms times 0.02 meters squared, which equals 2 times 10 to the minus 5th kilograms meters squared. Our velocity is equal to our angular velocity times the radius. In this case, the radius that we're dealing with is the radius of the peg, because that's where the rope is winding off of the yo-yo. Entering these values and terms into our equation, we get 0.05 kilograms times 9.81 meters per second squared times the height of the yo-yo is equal to 1/2 2 times 10 to the minus 5th kilograms meters squared times 80 radians per second squared plus 1/2 0.05 kilograms times 80 radians per second times 0.005 meters squared. Solving for our height, we get that our height is equal to 0.14 meters or 140 millimeters. Our next topic is rigid body kinetics using non-conservative work.